When is our exam? Monday. What's the cover? Starts with working energy, all that, all that. And it goes up through all the linear momentum and stuff like that. So we have our test 3 is next Monday. Doing lab as normal. Okay. And it starts with work energy up to and including linear momentum. Okay. So what I want to do today is, and again, what I'll do is the same format as before. On Monday morning during the class, I will ask if there's any questions on the exam. I will entertain questions until there are no questions. So if you have like some last minute questions that you have on something, you can ask them on Monday, or you can come by any time during the week. But if there are no questions, then we start new material. And then new material will be basically, we're going to start rotational motion like this, which is the last big major topic we deal with. Okay. So what I want to do is classify all collisions. So all collisions can be classified as either. Anyone know what they are? Maybe from high school? Okay, just elastic and inelastic. Is either elastic or inelastic. And just so you know, it's very hard to have elastic collisions. Almost everything in real life is always inelastic. You can have elastic and they're important. And I'm going to show you how to do with this. So let's write elastic here. And then an elastic here. Okay, and both of them momentum is conserved. So no matter what, I'd have P initial equals P final. This is P initial equals P final. So when you see these collisions are going to conserve linear momentum no matter what. Now here's the difference. An elastic collision, the kinetic energy before the collision and the kinetic energy after the collision are the same. Hey, what do you think then happens in inelastic collisions? They're not the same. You can think about that. You know, if you have two cars smashing together like this, okay, in the collision, look just before and just after, momentum is going to be conserved. Is energy conserved? Or kinetic energy is the same after the collision? Right, so I have the kinetic energy of this car, kinetic energy of this car, bam. Is kinetic energy of each car the same after them? If I add them up, is it the same after the collision? No, where did part of the energy go? Destroying the cars, exactly. Goes in breaking the glass, bumping, breaking the people inside to just destroy the car. That's where part of the energy goes to. A lot of the new designs on cars, they have what's called a crumple zone, which is kind of neat. It's an interesting idea. What's the idea of a crumple zone? Yeah, so basically what you are is, if you're in a car, that energy from the collision, you don't have to go into your body, because that means that you're gonna most likely die or be horribly, injured. And so what you want to do is you want the energy to go into basically collapsing the car. And so the car is designed to collapse so that that energy doesn't go into you. And so there's a region that you don't want any of that collapse to occur. And that's where you're going to stay. That's the idea of a crumple zone. It's a very clever idea. Okay. Now, this is kind of an odd thing. Which of these things do you think would be easier to deal with? Are these going to be easier, or are these going to be easier?
Much easier.
You think that this would be easier?
Yeah, this is energy.
Yeah, you'd think that that likely be much easier. I'm going to convince you these are actually significantly harder. Okay. These ones are actually going to be a lot easier to deal with. These are going to be first class pains in the rear. Okay. And what I want to do is explain why these are hard. And then I want to show you a very special case. Some people don't do this. I think it's a mistake. I'm going to show you basically how to deal with one-dimensional elastic collisions. Now, here's a little catch. What I'm teaching you will only apply to one-dimensional elastic collisions. And if you do this, it makes those problems infinitely easier. Okay, if you don't have to do what I'm going to show you, but then you're going to have a lot more work involved. So let's go and deal with this. So it turns out elastic collisions are harder to deal with. Let's ask why. Okay, so let's just I'll just make something here. So let's say here's an object like this. This is V1, this is M1, this is initial, this is V2 initial, this is M2. And then let's say after the collision, we have the following. This is before. And after. I'm just going to make this up. Okay, so if I said set this up, what would you do? Let's say this is an elastic collision. So what would you do for this? Well, you have to say P initial equals P final. So how do you write that mathematically? Okay, don't write down the following, okay? Could you say M1 V1 plus M2 V2 initial here equals M1 V1 final plus M2 V2 final? Can I say this? Obviously, by the way I'm wording it, you can't. What is wrong with that expression? That treats momentum as a scalar. Fix that. What would I have to include? And it's very important how you write things. I know that it sometimes seems like I'm being petty on something, but I'm not. It's actually really important. How could you fix that? You do X and Y. There's another thing. I'm lazy.
Magnitude.
Oh, that'd still be the scalar. Where's the vector in momentum? So how can I fix this? Done. This is true. That's correct. But that little symbol makes all the difference in the world. Okay, that little symbol is just not me being nitpicky. It's actually really fundamentally different. Because what does this say? This really says, remember this equation, really says P initial X equals P final X. And it also says then P initial Y equals P final. So this would split up into these equations here, M1 V1 initial X plus M2 V2 initial X equals M1 V1 final X plus M2 V2 minus X. And then likewise for this one here. Okay. Now, but you're going to get that equation in both elastic and inelastic. Now, here's where things get hard. What do you also then have for inelastic? I mean, for elastic. If it's elastic, kinetic energies are the same. So if it's elastic, I'd have to say KE initial equals KE final. Is that picking that up? Yes, it is. So what is your initial kinetic energy? What is kinetic energy always? 1/2 mv squared. So what is my initial kinetic energy? kinetic energy of this plus the kinetic energy of this. So I have 1/2 m1 v v1 initial squared plus 1/2 m2 v2 initial squared. And that would have to equal what? This kinetic energy. 1/2 m1 v initial, I'm sorry, v 1 final squared plus 1/2 m2 v final 2 squared. Why did I make life now just infinitely harder for me? I give you a hint, this is a math reason. I have these equations. I have these equations. Why are these equations not too bad? But this equation is going to be a first-class pain. I can't hear you.
There's a bunch of variables.
Yeah, there's variables in that one up too. Okay, there's something very wonderful about pulling out that cord and hearing silence. I like it. Okay. They both have variables. What's the point about this variable as opposed to this variable? Well, these are squared. So now I have a quadratic. I have linear equations and I have a quadratic. That quadratic makes life a lot harder. So this is a quadratic. And this makes life harder. Okay. That's why elastic ones are going to be harder to do. Now, there's going to be one special case, and this is important physics that I want to look at. Okay, I want to show you kind of a special way to deal with elastic one-dimensional collisions, and it turns out my cats really like these. And for some reason, when my cats write the third exam, some variation on this is always on the third exam. Imagine that. So I'm going to show you a special case. And then we can, oh no, I was going to say the dumb executive here. So once we actually get this one rule, we can actually then understand this. Okay. Okay. So even though elastic fluids are typically more difficult, there is one special case where they are not too difficult. And this special case, this case is 1D elastic motions. I want to show you what happens with these, and then I want to just do a whole bunch of examples so you can see them. All right, so the key here is going to be one-dimensional. What does it mean to be a one-dimensional collision? Yeah, they're going to smash together like this and go like this, or smash like this. They're going to somehow, they're only going to have motion this way. You're not going to have two things coming like this and then go off like that. Okay, it's just boom, boom, or boom, like this. Could also then explain something when I was younger and my father and brother were teaching me how to shoot. I wanted to shoot, put a rock on a fence post and shoot it off. And my dad says, we're not shooting rocks off a fence post. And I thought Dad was just being a killjoy. Turns out Dad knew a little more physics than I did, even though he didn't realize it. And there's a reason why you do not shoot rocks off a fence post, and we'll see why. Even though that would be cool. Okay, so let's go and see what we have here. So we will see that in 1D elastic collisions, I'm giving you the result here, then I'm going to prove it. We will see that 1D elastic collisions, the relative velocity between the two objects changes sign. So what we're going to find out, we're going to see that V relative initial equals minus V relative final. And let me explain this. So at some point, you probably run on bumper cars. Now, when you're on a bumper car, what do they tell you to never do? Head-on collisions. So what does that guarantee that every child does? Head-on collisions. You're in your little bumper car, and your buddy's coming at you this way. So with the bumper car, the collision is up. This is going to be approximately elastic. So you're right. So you're going at your buddy, he's coming at you. And let's see I'm here. And let's say I see my buddy coming at me at 10 meters a second. So that's what this is here. So I see, according to me, my buddy is coming at me at 10 meters a second. After the collision, if it's a 1D elastic collision, I'm going to see my buddy going away from me. That's the minus sign. But what is this going to be? This is going to be at minus 10 meters a second. So what I'm going to do is if I see my buddy coming at me at 10 meters a second after the collision, if it's a 1D elastic collision, I'm going to see my friend going away at minus 10 meters a second. That's what that means. Okay? I want to show you why this is the case. And the advantage of this is mathematically, this is going to be a linear equation. So you're going to end up with two linear equations instead of a linear and a quadratic. And this is what is going to make life easier. Okay? Proof. Just so you can see here. I haven't looked at test 3 that my cats wrote last semester. Oh, hey, imagine that. And part 2, number B. It looks like there might be an elastic 1D collision. I wonder what's going to happen in your exam on Monday. I wonder if there will also be a 1D elastic collision. I can't wait to find out whether you will also have a 1D elastic collision. So proof. Okay, so to do the proof here, we're going to assume, obviously, a 1D elastic collision. So what I'm going to do is this is going to be M1. This is going to be V1 initial. I'll just call this V1 here. And this would be M2. And this would be V2 initial. So this is V4. Okay, now you might say, well, wait, if they're colliding, why isn't this one going this way? Okay, the reason why is if I have this one going this way, I'm introducing a word minus sign early in the derivation, and that can be weird. It's going to be a lot easier with the signs if we just assume everything's going this way. For this to collide with this one would be moving faster than this. So this is just to make all the signs work out easier. And then after the collision, and again, this is normally when you do something, a derivation, just assume everything is either going up or to the right, then you don't get these word minus signs coming in. So after the collision, I'm going to say that this one has some velocity V1 final. This has some velocity V2. That all fit. And it did. Okay, so this is after the move. So, what's conserved? Linear momentum. So I'm going to say P initial X equals P final X. So what is from this picture here, what is my initial X momentum? So I have this one, M1, V1 initial, which I'm just reading as V1. And then this one here, M2, V2 initial, which I'm just reading as V2. Then the final linear momentum is what? It's the same thing on this side. So this is M1, V1 final, plus M2, V2 final. Do the masses cancel? Excuse me. They do not. Why don't the masses cancel?
Do you have two different masses?
Two different masses, they don't cancel. Now, what I am going to do, just because, now, the only reason I'm doing this is I know how I'm going to use this result. I'm going to take all the M1s over here and all the M2s over here. So if I do that, I can write this as M1 V1 minus M1 V1 final equals M2 V2 final minus M2 V2. And I'm going to factor out the M1 on the left and the M2 on the right. And again, this is only obvious because I've done this derivation before. Whoever did this derivation the first time must have felt terribly proud of themselves because it's a very slick derivation. I can rewrite this as M1 times V1 minus V1 final equals M2 V2 final minus V2. Now, if this is elastic, what else has to be the case?
Yeah.
Yeah, so I'd have to say KE initial. Equals KE final. From that picture, what is my initial kinetic energy? 1/2 M1 V1 squared. Keep going.
Plus 1/2 M2 V2 squared,
Equals
1/2 M1 final squared,
M1 V1 final squared. Let me finish it up.
1/2 M2 V2 final squared.
Yep. Okay, what cancels? All those stupid Haskell out. That's good. And then I'm going to do the same thing. I'm going to take all the M1s to one side, all the M2s to the other side. And again, why am I doing that? Because I've done this derivation before. I'll factor out the M1 here. And I'll factor out the M2 here. Okay, now here's the non-obvious part. I'm going to write this square term and then this square term as two linear terms being multiplied by each other. So I'm going to write this like this. Again, you could say, how would you know to do this? Well, I only know to do this because I saw somebody else do it. If I had never seen this, I would have not known to do this at all. Okay, so what two things would I have to put here? And it's going to involve V1 and V1 final, such that if I take this times this, I have this up here. That sounds like a great thing. So this one here, I can write this mess here as V1 minus V1 final times V1 plus V1 final. Right? This times this is this term. This times this is this term. And then the cross terms cancel. Make sense? Now then what can I write then this term as?
Same thing.
The same thing, but with the V2F coming first. Yeah. So this would be V2F minus V2, V2F plus V2. Now magic occurs. We get a beautiful cancellation in Y. You might want to look at the top of the board. What do I know about this term right here? This term right here is equal to this term right here. create a slip. So that whole term here cancels that whole term here. Again, I would have felt very proud of myself if I did this for the first time, but I didn't. But what am I left with? I'm left with this term here. V1 is V1 final equals V2 final plus V2. So what I'm going to do is I'm going to take the initial values over here and the final value over here. So I write this as V1 minus V2 equals V2 final minus V1 final. And I'm going to define this right here to be the relative velocity before the collision. The first velocity minus the second velocity, that's my relative velocity. Now, so V1 minus V2 is this one here. So to write this one here, I have to pull out a minus sign. So I can write this side here is minus, parenthesis, V1 final minus V2 final. So then the side here is V relative final. So therefore, I have my V relative initial equals minus V relative final. So how have I incorporated kinetic energy in the derivation of this expression? And that's going to make life a whole lot easier. So let's do an example of this. Then I want to explain how the Newton's cradle works. Questions? So let's do this. Okay, let's take an example. Okay, so I'm going to have a mass here. This is 5 kilograms. This is, let's think, this is 10 meters a second. This is going to be 3 kilograms. Let's say this is 4 meters a second. This is before. And then after the collision, I'm going to call this V1 final. And I'm going to call it for the 3 kilogram mass. And if I'm going to call this V2 final. I want this is after. I want you to find V1 final and V2 final, assuming at 1D collision, 1D elastic collision. So I have 2 masses here. We're assuming a 1D elastic collision. Afterwards, we have no idea how the velocities are going, so I'm just randomly drawing them going to the right. Now let the signs determine everything. I want to figure those out. Okay. You tell me what to do. And why would you say that? That's completely correct. Okay, I was thinking momentum.
Oh.
But what you said is true.
Because it's an elastic equation.
Whenever you see things collide, you think collision. So when you're doing one of these physics problems, if there's a collision, you think conservation of linear momentum. Linear momentum, collision, linear momentum. Just put those two together in your head. Okay, so you're going to say P initial X equals P final X. Now here's something you're going to rarely hear out of me, okay? Usually with these problems, put the numbers in early on, okay? Again, sounds like I've gone insane or been basically replaced by some pod person. And maybe I have. Okay, but this is just to make life a lot easier. Okay, so what is your initial momentum in this case here? So I'd have M1 times V1 here. So I'd have the 5 times 10 plus 3 times 4. Yeah. What? Don't do it this way, because if I do it like this, what am I saying about this one? It's going to the right. You have to put a minus sign there because momentum is actually a vector quantity. Okay, equals. Now, what would I write for the final momentum?
5v1.
5v1 final plus
3v2 from.
3v2 final. Let's crank this out. So this is 15 minus 12. Oh, well, that's a rotten value. Okay. So this is what? 38. Oh, 38. Oh, sorry. Okay. Oh, wow. Okay, would anyone be opposed if I change the value? Well, let's just keep it. Sorry, I will. Sorry. Okay. So this is 38. So you have this is going to be 38 times V1 final plus 3 times V2 final. How many unknowns do we have there? 2. So how many more equations do we need? 1. We needed 1 more equation. 2 equations, 2 unknowns. Now, normally, what would you do if this is elastic? You would think what? You say the initial kinetic equals the final kinetic, and you can do that. There's nothing wrong with it. The problem is what's going to happen with the V1 final and the V2 final? They're going to come in squared. So you have to solve for this, put it into the quadratic, put it into the energy equation. You get a quadratic, then you'd have to solve the quadratic. You can do that, but it's a whole lot harder. It's easy to make a mistake. Or we can now use our handy dandy result. What's our new handy dandy result? The relative velocity flips. So you can use KE initial equals KE final. But this approach is more difficult. So therefore, since we have a 1D elastic collision, we will use V relative initial equals minus V relative final. And how do we define V relative again? V1 minus V2. Now you could say, shouldn't it be V2 minus V1? That's perfectly fine as long as you do both the same on both sides. So if you want to say V1 minus V2 here, say V1 minus V2 here. If you want to say V2 minus V1 here, say V2 minus V1 here. However you define it this way, define it the exact same way on this side. It doesn't matter. But I'm going to do V1 minus V2 because I'm a 1 minus 2 kind of guy. Okay. So you tell me what to put in for this then. What is my relative initial velocity? This is going to be our V1 minus V2 minus V1 final minus V2 final. So V1 is what? 10 minus, what is my V2? Minus 4. Equals just the minus V1 final minus V2 final. So this gives me 14, sorry about that, minus V1 final plus V2 final. Okay. Now I have 2 equations and 2 unknowns. Okay. So how do I solve this? I can plug it back in. Or if I wanted to, what can I do?
You could add the equation.
If I call this A and if I call this B, I could add them, but I want to add them in a certain way. No, it'd be nice if I could get rid of something if I add them.
Multiply by 5. How do you get?
Which one? If I multiply this one by 5 and then add these 2, what happens? Fill this guy here. So that's what I'm going to do. Again, you don't have to do it that way. You can solve this one for V1 final my V2 final, and put it in here and crank it through. It's the same thing. So what I'm going to do is I'm going to say 5 times A plus B. I'm going to work out that. Then I take my equation A here and multiply it by 5. Then I'm going to add to that equation B here like this. So what does this give me? This gives me 5 times 14, which is 70. Sorry about that. Plus 38. Now I have minus 5V1 final. I add it to positive 5V1 final. I get the 0 here. Then this one is going to give me what? 5 times V2 final plus 3 V2 final. So this gives me 8 V2 final. So this gives me 108. Oh, wow, that's bad. Equals 8 V2 final. So my V2 final is 108. Yuck. Bad. Okay, what was that? You worked it out?
13.5.
13.5. Okay, so what is my V1 final then? I put it into here or into here. I'm going to do one of them. Which one's going to be easier? Yeah, because I don't have these with numbers in front. So I'm just going to take this one here. So if I put it in there. What is that going to give me? I'll take the V1 final over here and the 14 over here. I'll just leave it like this. 14 is this plus 13.5. So my V1 final is 13.5 minus 14. This would be minus 0.5. Did that work? Did my relative velocity flip? Yeah, my V relative final. Or this is going to be V1 final minus V2 final. My V1 final is my buddy here. My V2 final is my buddy over here. So this is minus 14. So before the collision, the relative velocity was 14. After the collision, the relative velocity is minus 14. That makes sense? You get the exact same way doing it in terms of the kinetic energy, but with significantly more work. Okay. Questions? Okay, let's take a special case here. Let's take the special case. Special case of a 1D elastic collision where one mass is initially at rest. You're going to get a lot of mileage on this. Oh, just so you know, I'm going to impart all my pool knowledge to you. Okay, for some reason, when people find out you're a physicist, you'll hear things like, well, you must be good at pool. Well, I can barely spell pool, okay? And I can assure you I'm not. I know about 2 things in pool. I know 2 things in pool. And I'm going to impart them both to you. One will be today, one will be tomorrow. Okay, so let's actually do this. So let's say this is going to be, yeah, I'll make this. Here's M1. And this has some velocity, I'll call it V0. And here's M like this. This is at rest. Before. And here's the after. The after. Actually, I don't know if I call this M1 here in this capital, I'm not really being consistent. I'm going to get rid of that one here. So after the collision, I'm going to call this V1 final. Call this one here V2. And I want to find V1 final and V2 final. You tell me what to do. I'll give you a hint. You are pros at this. That sounds like a great thing to do. What is my initial momentum?
Little one. No,
V naught plus.
zero.
Sure. What is my final linear momentum? Sounds great. So that gives me this equation here, and I get to put a box around it. It's always fun putting a box around it. Now, since it's elastic, I could say the initial kinetic equals the final kinetic. That gives me a quadratic, and that has a mathematical property called yucky. Okay, what's a new fancy way of doing this? That's a whole lot easier. The relative velocity flips. The next part, I'm going to say V relative initial minus V relative final. From that picture, what is my initial relative velocity? Now this would be V naught minus 0 equals minus, what's my final relative velocity? Minus V1 final minus V2 final. So this gives me V naught equals minus V1 final plus V2 final. Okay, what will I now do?
Plug that in.
Yeah, I'm going to solve this for either V1 final or V2 final. I'm going to solve this for V2 final and put it in here and then solve for V1 final. So if I solve this one for V2 final, I get V2 final equals V naught plus V1 final. I'm going to take this right here and pop that right into here. So this gives me M V naught equals M V1 final plus big M quantity V naught plus V1 final. What do I do now? Yeah, so I'm going to get all the little M's together and all the big M's together. I'm sorry, I'm going to get all the V naughts together and all the V1 finals together. So I'm going to take this from over here. And then I'm going to factor out this V1 final from here and from here. What do I do on the left?
Cancel.
Factor out the V naught. And divide through by this guy. We get V1 final. So this is one of them. How would I get V2 final then?
Before we get into the second equation.
Yeah, if I take this and put it back into here. What do I get? This is going to be the important one of these. This is going to explain a lot. So my V2 final is V naught plus this necessary. What would I do with that? Tell me why you wouldn't leave it like that. Just should make, I want you to start looking at equations. And if they're left in a certain way, I want you to start cringing because it just looks bad. You can pull out the V naught, but then one more thing. It screams to have it done.
Me too.
Scooby, do we say ramen or Ramator, Reggie? Common denominator, Shaggy. Excellent. See, you're mastering Scooby-Doo already. So I multiplied the top and bottom of this term here by little one plus big M. So I'm going to pull out the V naught. This term's here. And then I did a common denominator here, so I'll have to multiply the top and bottom by that same quantity. Like this. Then what happens? Well, the big M's cancel, the little ones add. I get this. The important thing is this guy here. Let's look at the result. There are 3 cases for V1 flow. You look at this equation here. What are the 3 cases? Has to do with the masses.
Masses are.
That could be one of them. I could have the case of M equaling big M. What happens in that case then? Yeah, if little m equals big M, if these are the same mass, V1 final is 0. What about V2 final? These masses are the same. The bottom then becomes 2m, so this, they cancel here. So this gives V naught. Explain this in pool. This is one of my pieces of pool knowledge. Develop it in a little pool. Cue ball here. Just not cue ball. Regular ball here, cue ball here. You hit the cue ball, and let's say that this goes here and hits dead center, this pool ball here. Okay, if you don't put in any English refers to basically the rotation of the ball. If you neglect that, what happens in that case? This comes along with a certain velocity, hits the cue ball hits the other ball, the cue ball stops, and then the other ball goes away with that same velocity here. Right? That's what's happening with this. I have this. Okay, what is this collision approximately? It's approximately elastic because you have steel balls, and steel balls, when they hit each other, they're not going to deform at all, or very little. You're going to lose a little bit in vibrations with sound and stuff like that. But this is at rest. Here's the other ball. This comes down here and now has kinetic down here. It's going to smash in here. These have the equal mass balls. So what's going to happen here is that this is really this case here. So what happens? This one comes this way, collides elastically with this one. This one stops and goes up. Then this one comes back down this way. And what does it do when it collides? Another elastic collision. This one stops, goes back up. And that's why you have this type of action like that. Does that make sense? Okay, what's your other 2 cases?
And small n is less than big N.
I have this. Now, what's important about the V1F? That this is smaller than that.
It's that has to be big to make the big one.
The bottom is positive. What about the numerator?
Negative.
It's now negative. This is negative here. What about my V2 final? No matter what, V2 final can only be positive. Okay. So what does that mean? Right, if I had, let's say, a big ball here, if I had, like, let's say, a marble like this, And I whip my marble at that big ball. Let's say it's an elastic collision. What's that little marble going to do? It's going to be coming back at me. Why did my father not want me shooting rocks off a fence post, even though that would be cool? The collision isn't elastic, obviously, but it's still you have a physics occur at some level. There'd be a chance since the bullet would be much smaller than the rock, most likely. There'd be a good chance that that bullet could come back and hit me, which is why Dad said no. Dad, even though that would be cool. Okay, now what's the other case?
Big M is,
Little m,
little M is greater.
bigger than this big m, and then this right here is in positive. So if I have a little marble here, and if I have a bowling ball, and if I whip this bowling ball at that marble, if that's an elastic collision, that that little bowling ball's not coming back at me. Everything's just going this way. Okay, well, more of this tomorrow. Have a good day. Sorry for going a little late.